Okay, recall in the last discussion we talked about eliminating p. So up here in this set of equations you've got linear momentum for x and y, you've got an incompressibility constraint. This creates problems if you want to take the inverse. It's not positive definite. It may create an instability during inversion. So if you want to eliminate p, a way to do that is introduce what's called a constraint. So you put a constraint to make sure that this stays incompressible, but you can do this in special ways that eliminates this issue with inverting this matrix, right? So we're not going to solve p simultaneously with the velocities. We're going to do it in a constrained manner. So the best way to describe this is through a few equations and an example. For more of a details, look in section 4.6.4 in the book. But essentially, we start out with a somewhat abstract definition. We want to minimize some function of x and y subject to the constraint g of x and y is 0. Physically, what this means is this minimization of f. I'm using just a scalar function, but if we were to really solve the finite element problem, this would be the momentum equations in x and y. This would be your velocity in the x. This would be your velocity in the y. So there's no pressure that we're solving here. Instead, we're going to constrain this to be 0. So this is basically your continuity equation, which makes sure the pressure is adjusted so that incompressibility is satisfied. But we don't do it simultaneously. Instead, what we do is introduce this other function that includes the momentum equations and then this constraint, and we introduce this unknown constant. So this is what's called a Lagrange multiplier. So it turns out this is exactly the same thing as your pressure in the incompressible fluid dynamic problem, but it has broader context and a very wide variety of problems. It may range from optimal control theory to other types of numerical problems. So this is called the Lagrange multiplier method. So basically you take the variation in this and you set it to 0. So one is, here's your what's the same thing as momentum in x, momentum in y, and then this is due to this incompressibility constraint. Alright? Now, that's one way to do it, and that's often used in theory, particularly optimization problems. Numerically speaking, what's normally done for finite element problems is called a penalty function method. And in this case, you introduce this other function, f of p. You still have this function of x and y, but now we take the quadratic on this constraint and we introduce a weight parameter. This is something you would define in the finite element problem. So you'd make this very big to make sure it's close to being incompressible. So the bigger you make this, the closer it will become to being exactly incompressible. Unlike in the above Lagrange multiplier method, this is an unknown. Here it's just a constant you put in the finite element problem. So since this is assigned, you take the variation here, you just have two equations. And if you remember, that's what we're after. We just want to solve the first two equations for the velocities and not the pressure. And that's what we get. So if you want to correlate these two, you approximate the Lagrange multiplier with, here's your Lagrange multiplier, g times this constant gamma. Okay, so more specifically on an example, doing this on a traditional finite element problem is just unwieldy if you want to do this by hand. So instead, the same thing applies if we're dealing with a arbitrary polynomial. So let's just say you have a function of x and y, this polynomial. You want to minimize it given this constraint. Okay, so we're just saying we have this arbitrary constraint equal to 0, and we first use Lagrange multiplier method. So we again introduce this form given in the previous page. Take our derivatives in x and y, set it to 0, take derivative on the Lagrange multiplier, and now you have 3 equations, 3 unknowns. So you can solve all. Alright, now that's not normally used in the finite element problem. What is used is penalty function. So here we introduce this functional form, take our derivatives in x and y, and we solve for x and y. But instead of putting in a constant initially, we solve for this in terms of the constant for x and y. I've used this subscript gamma as being an approximation of the true solution. And here's what you find. So what's interesting is if gamma goes to infinity, being very large hydrostatic pressure, if this was a fluid problem, x goes to -3, y goes to 2, lambda goes to 7. Matches Lagrange multiplier. So in the limit, as gamma becomes very large, this becomes exact. And of course, you're not going to put infinity on a computer, but if you make this relatively large to your other field equations, it's a pretty good approximation.